Okay, so just to clarify, and if there's any tech issues still, talk to me about it after class. But just to clarify, pre-class assignment is reading, usually videos, and tied to those questions. If for some reason the videos aren't loading, just go straight to the textbook because they're in there somewhere. As long as you find the same video. The content's also in there in text if you want to just do it that way. Those are one try, but multiple attempts per question. I think it's just like 2. So if you get it wrong the first time, maybe look a little deeper and then try again. So that's done. That's due like the morning before class, or the morning of class rather. And then the after class assignments, dynamic study modules, those are adaptive, so it's fine if you get stuff wrong. It'll just keep asking you questions until you've passed all of the topics that are listed. So those are due next Thursday morning, I guess, Wednesday night, Thursday morning. And you can do about a third of it today. Some people were like confused and they just did the whole thing already. So apparently it's not that hard, okay? So that's, well, but you didn't have class yet. Did you try to do the whole thing?
I did try to.
Okay, well, it's okay then, because if...
I got through it, but I don't like how it gives you 2 questions for every question I failed.
Oh, yeah, that is me.
I got it all.
I feel like that happened to one of my kids one time. Okay, so let's go ahead and jump in. I rearranged the slides in my head a little bit in my last class. I think you guys have the advantage because you're my last class of the day. So I might be a little bit more tired, but I have the structure kind of more clear in my head of how I want to give it to you guys. So I'm going to start in with kind of 2 main things that we're focusing on today and that I obsess about a little bit throughout, I was going to say the semester, but really the year. So the first being energy and how that's tied into chemistry energy. Chem 1, okay, yes.
Yeah. There's like no spots anywhere. I'm just like...
Here's an extra, there's a spot there, and then also there's an extra chair. Aren't you in my morning class? Somebody that looks a lot like you.
No.
Okay.
I mean, that's probably at least not. Yeah.
Okay. You guys all have that, messy hair.
Yep.
One of my twins has that. I told him, I'm like, this weekend, this little bit on the back, that's going away. Whether I have to chase you down with scissors. Okay, so we're going to talk about classifying matter, but that's mostly so that we're all clear on terminology. But these 2 things are things I'm going to harp on all year long, okay? So I want to start in on energy because it's important for understanding states of matter. Then we'll do classifying matter, and then we'll kind of go on to the unit stuff, okay? So I'm going to start us on this page, I believe. Yep. Okay, so usually I do this with a marker, but I've got this nice picture here now. So you've got a weight, you hold it off the side of a building, and you drop it. Obviously, we all know that it falls, but the thing we want to talk about is why does it fall? How does that relate to potential energy, and then how does that translate into what happens in a chemical system? So be clear on the fact that when you have 2 things that are attracted to each other, so in this instance, it's 2 objects, and they are attracted to each other. The one with the large mass creates an attractive force on the one with the smaller mass, okay, the gravitational force. So when that happens, the further apart they are, the higher in potential energy that object is, okay? So this up here is high potential energy, and down here, I'm just gonna underline it because it's written right there. So high potential energy and low potential energy, and that's due to the fact that there's an attraction that exists. Okay, now when you go from that high potential energy to the low potential energy, that energy has to go somewhere. And hopefully from physical science, physics, whatever, somewhere middle school, or high school, you know that energy isn't created or destroyed, it's just transferred. So, or changes its form. So in this instance, that energy comes off as kinetic energy. So energy of motion. So the object moves, right? Kinetic energy, the energy of motion, is closely tied to thermal energy, which is basically, we can just think of as temperature. And in chemistry, this becomes really important because temperature is just, and this is true of anything, we just don't usually think about it on a macroscopic scale. So macroscopic is like what's going on right here, right now. Microscopic or atomic level would be thinking of it in terms of atoms and molecules. So on a macroscopic scale, we don't usually think of temperature as this, but on the atomic scale, temperature is just how fast the atoms or molecules are moving. So atoms and molecules are always vibrating, even if it's like in a solid substance. There's a little bit of motion there. But let's think of the air in here, oxygen, nitrogen, a little bit of argon, carbon dioxide, those molecules have a certain amount of motion, but outside they are moving faster. And that is why that's how we interpret that motion, is by how it feels, how that energy is transferred into our skin. Okay, so movement, kinetic energy, is exhibited in molecular motion, and then that's tied to its temperature. Let's see. So I'm just going to add in there molecular motion. Okay, so the faster molecules and atoms are moving, the higher the temperature will be, and that is equivalent to saying the kinetic energy is higher, right? Energy of motion, kinetic energy, movement of the molecules. Okay, so how does this end up tying into atoms and molecules, or like compare to atoms and molecules? So unlike in a macroscopic setting where we're primarily focused on gravitational force, in chemistry we're focused on electrostatic forces. So this is the attraction between positive and negative, and literally everything in chemistry is dictated by attraction between positive and negative. So this could be, the bigger a positive charge is, the better it is at attracting a negative charge, and that lowers the potential energy. This could also be repulsive forces, because in any attractive thing you also have like a reverse, the equivalent, or the reverse being the repulsive forces between negative and negative, or repulsive forces between positive and positive. We'll just keep it simple for now and keep it in terms of attractive force between positive and negative. And the simplest form of that is the attraction that exists between a nucleus and its electrons. So basic structure of the atom. In science, we're always trying to form models that describe reality, and we get better and better at them. So this is not always what the model of the atom looks like, but it is currently, at least what we tell you the atom looks like. It is pretty much. I think of it slightly different, but we won't go into that till much later if it's useful. So not the nucleus like in biology in a cell. That's like thousands, millions, billions of atoms and molecules. We're talking about the nucleus of an atom. So we have very, very small particles. We're talking about protons and neutrons. Protons are positively charged, neutrons are neutral charged. I've heard the analogy of like the nucleus would be like the size of a baseball, and then the entire city of Pittsburgh would be the atom. So it's very concentrated in the center of the atom, and the vast majority of the space in an atom is empty space with the electrons interspersed in that space. Okay, so the electrons are like that blue region, electrons plus empty space, and then the nucleus is in the center. So you have electrons that are now attracted to the nucleus, and just like in the analogy with gravity, the closer those particles are to each other, the lower the potential energy. So the weight is lower in potential energy when it's close to the thing that it's attracted to. And that's true in atoms and molecules too. This electron is closer to the nucleus, and so it is lower in potential energy. The one up here, higher in potential energy because it's further away from the nucleus. So we're not going to do a whole lot with this idea right now, but it is just essential as we move forward to understanding that this relationship exists. So we are going to talk a little bit about energy changes in phase changes, but this idea is going to become really pertinent as we move forward. Similar to the example with the weight, if the electron moves, let's say, from a high potential energy to a low potential energy, that energy also has to go somewhere. It's not leaving as kinetic energy. We'll talk about what it does leave at later at the end of the semester pretty much. But that energy change does have to occur. But there's always this driving force for things to go to a lower potential energy. That's why the weight falls down, right? There is a force pushing it towards a lower potential energy. Same is true in an atom. All right, so let's go back to the top, talk about phases and the energy changes associated with those. I almost wish I had like rotated this so that we could have kind of an energy diagram with gases up here and liquids here and solids there, but that's how I'll draw it. So this is like an energy scale that I'm drawing for you. Okay, and when we go from a gas to a liquid to a solid, we're going down in potential energy. All right, and then in the reverse, when we go up from a solid to a liquid to a gas, we're increasing in potential energy. So just like in the examples here, when we decrease in energy, that energy has to be released. When we increase in energy, some kind of energy has to go in to make that happen. So these are not chemical bonds, but the particles in a solid are attracted to each other with forces that we'll talk about at the beginning of semester 2. Okay, doesn't matter right now. There are attractive forces though that keep these particles together. And as it moves to the liquid phase, those forces start to get loosened, I like to think of it. And then by the time we get to a gas, those forces are completely broken. So we've got things that are attracted to each other, we're pulling them apart. That requires energy, just like if it was a nucleus and an electron, to move them apart would take energy. Low potential energy, higher potential energy, so it takes energy to pull them apart. Also, just think about them as being attracted to each other. I've had students in the past that have thought of it like magnets. Like it takes energy to pull two magnets away from each other, right? And as soon as you let them go, assuming they're close enough, they're just gonna like suction back to each other, right? That's what being attracted means. So the same thing happens in solids, is that those particles are attracted, and so it takes energy to break them apart. You can see this pretty obviously if you were boiling a liquid. In that process, as you boil it, you're turning a liquid to a gas, and so it takes energy. You have to stick the pot on the stove and turn it on. You put energy into that system in order for that phase change to occur. So just like the general idea of getting what phases look like, what their properties are, but understanding what it takes to go from one to the other. Okay, so overarching themes of energy, tendency towards low potential energy. This exists. Differences in potential energy exist because of attraction or attractive forces. Oh, I can't spell, just so you know. That's like a big joke in our house. My kids will be like, Mom, how do you, oh, never mind. Google, spell such and such. It's really embarrassing, but I'm good at other things. So attractive forces are what dictate that energy. And then going from a low potential energy to a high potential energy is going to require energy. And the opposite would release energy. So these are kind of like major themes that we're going to repeat over and over. I know it doesn't feel like there's a whole lot of context there right now. That's because we're just introducing things. Okay, so this is what I mean about basics. I'm not gonna like describe to you the properties of solid and liquid and gas. I'm not gonna like restate the stuff down there and just read my slides. Okay, I might have said some of that in different words, but mostly I just have notes up there to be like, remember you read this in the textbook and you already know this. Okay, the next kind of big idea, not even like big idea, but just terminology that we need to be comfortable with, relates to how we classify matter and then also how we talk about its properties. So we're going to talk about chemical and physical changes, and then we'll kind of teach you the approach to how we solve problems and then apply that more next class. Okay. So these 4 terms are not individual terms we use. Usually we use a combination of them to describe any one substance. All right? So atoms are these individual building blocks. I had this idea this morning about Legos. So you've got a pile of Legos. Those are your atoms. You can put them together and connect them in different ways. You can break them apart and make something new, but you don't really break apart the Lego itself. I guess you could, and there are little bits of plastic and little different things that make up the Lego, but we generally keep the Legos all together, right? So we think of these as the building blocks, okay? There are a lot of different types of building blocks, and we call those the elements. So periodic table on the back, can't really see it very well. I'll open it up on here as well. So if it's listed on here in its own little block, it's an element. A couple things to note. There are ones that have 2 letters, and the second letter is always lowercase. So for example, cobalt is C lowercase o. That is an element. CO, both uppercase, is carbon and oxygen. That is a molecule. That's carbon and oxygen bonded to each other. So just take note of that so you don't get confused in the future. And if we write them together like this, we're implying that they're bonded to each other. Okay, so each of those elements has its own particular properties, and we'll talk about that eventually in the next chapter or 2. When we look at these examples, though, so the red ones here represent oxygen, the white ones represent hydrogen, okay? In this particular example, though, we've got 2 oxygens bound to each other and also 2 hydrogens bound to each other. So they are a single type of atom, but there's 2 of them. So we don't actually call it an atom because that implies it's singular, but it is an element because it's only one type of atom. They're both oxygens. So we would call this an element, but we would also call it a molecule. So once we start pairing things up, it's not an individual atom. And if they're of the same, I can guarantee you that they are molecules. But to confuse things, not all molecules are obviously made of the same atoms. So there's this example of water here. That is also a molecule. In that instance, though, it has 2 different types of atoms. So it is not an element. So these guys up here would be atoms. They are also elements because they are individual. They're not tied to each other, right? The oxygen is an element. It is an atom by itself. The hydrogen is an element. It is an atom by itself. In the next one, the oxygen O2 is an element because it's just that one type, but it's a molecule because there's 2 atoms bonded together. I'm going to go back to the periodic table really quick. So the reason why we have those 2 shown is because there are 7 different elements that when they appear in nature by themselves, they come in pairs. So they're called diatomics. And don't ever memorize anything in, if you can help it, in isolation. If you use the periodic table, there's a lot of visual tricks that help you to memorize things. So the 7 diatomic elements form, it's hydrogen over by itself, and then they form like the shape of a 7. So what I mean by this is that if they are by themselves in nature, not like in a compound like water, H2O, obviously there's just one oxygen there. But if it's by itself, hydrogen appears as H2, oxygen appears as O2, and that happens with these others as well. So N2, F2, Cl2, Br2, and I2. Okay? You'll have to memorize those eventually, but don't just memorize them, just see where they're at in the periodic table. Okay. Back to this. Okay, so compounds. Compounds is a general term for anything that has 2 types of atoms or 2 elements in that substance. 2 or more. So water would be classified as a compound. This other example here, it looks like I have a line, but I didn't save the title. So that's supposed to be sodium chloride, which is just table salt. But you guys can tell, hopefully, that they look different. The water exists as a little entity with 2 hydrogens stuck to it and an oxygen. So we use the formula H2O when we write it. So 2 hydrogens, 1 oxygen. But there can be lots of little water molecules. In fact, let me draw them instead of writing it as a formula. Let me draw it as a structure. So let's say we're in the liquid phase and we have all these little water molecules, or the gas phase for that matter. They still are their own little unit. It's like a water molecule here, a water molecule there. Even if they're attracted to each other in the liquid phase, they still exist as individual units, and we call that a molecule. So the term molecule is only applicable to things that have a particular type of bond, a covalent bond, that forms its own little units. Now, you don't know yet how to differentiate between a covalent and an ionic. It's not hard, but we won't talk about it formally until chapter 3. But if you have a picture like this, you can see that water is its own little entity. When we look at sodium chloride, which has ionic bonding, it does not form 1 sodium and 1 chlorine the way water forms 2 hydrogens and 1 oxygen. It forms this big crystal, this big mass of sodium ions and chlorine ions. When we write the formula, we're implying that it's a 1-to-1 ratio. Like there's the same number of sodiums as chlorines, but there's not just one of each. It's this big mass. So that's not appropriate to call that a molecule. Okay, so the only way at this point you would be able to differentiate if a particular compound is a molecule or not is by looking at a picture. Okay, so water would not be an atom because there's 3 atoms in water. It would not be an element because there's 2 different types of atoms. And it would be a compound because there's 2 different types of atoms. It would also be a molecule, that special type of a compound that exists as its own little entity. We'll see other pictures in a second of molecules, and you'll be able to differentiate them. Sodium chloride, on the other hand, would just be a compound. Yeah?
What was the name of the bond within a molecule?
Covalent. Okay, so all of these examples are applicable to pure substances, so like a glass of water, a spoonful of salt, right? A container that contains oxygen in it, right? Those are individual types of things. Another way of saying that, if we look at this flow chart, is that they have there's no variability in their composition. So like if I have a glass of water it's water here and water here and water here and water there, it's all water, right? If I have a glass of salt water, there's water here, there's salt there, there's water here, there's salt down here, and more salt and more water, right? There's variability in the composition. It's a mixture of multiple pure substances. Okay, so what we just talked about was pure substances. So the example they give here is that it can be a pure substance that's an element, or it can be a pure substance that's a compound. So we could throw in under the element category, we could add in O2 as well. They give helium here. In the compounds, they give H2O. We could also throw in the NaCl. That's still a pure substance. It is a compound, it's just not a molecule. So the other side of it is mixtures, which is combining two or more pure substances. So I'm sure you could think of a lot of examples, because basically anytime you throw any two things together, it would be a mixture. So like making cookies, that's a mixture. Even the sugar that you add in the cookies, that's a pure substance, but the butter that you put in is a mixture in and of itself. Butter has a small amount of water, it has like stearic acid in it, it has lots of different versions of lipids, fats, that make up the butter. So the butter itself is a mixture, the sugar is a pure substance, the salt's a pure substance, the baking soda is a pure substance. You can add those all together and make a new mixture that is the cookie dough. Okay? So anytime you're combining a pure substance, that's going to be a mixture. One easy way to tell if something's a pure substance is if I can write a chemical formula for it, like H2O, NaCl. Baking soda is NaHCO3. Okay, if I can write the chemical formula for it, it's a pure substance. Baking powder, on the other hand, I think is some sort of combination of, I want to say it's like cornstarch mixed with baking soda, mixed with like aluminum bicarbonate. I can't remember. Anyway, so baking soda is a pure substance. Baking powder is a mixture because it's a bunch of different substances mixed together. Okay, and then further, when we classify mixtures, we classify them as heterogeneous or homogeneous. So basically, if we can look at it at the atomic scale, just like we have a picture here, we want to know, is it uniform throughout the substance or not? So if I think of this on a macroscopic scale, it's going to be a little bit harder to tell. So let's start with the pictures. Like if I take this chunk of sand water, it's mostly sand and a little bit water. If I take this chunk, it's a little bit sand and mostly water. If I take this chunk, it's all water, right? It's not uniform. But if I look at, I would actually use salt water as a better example, because I don't like this as much. But if I looked at salt water, it's pretty much going to be consistently sodium ions, you don't have to know why that is, never mind, salt and water mixed in a way that is consistent throughout. So that if I take a spoonful of it, and you could tell this by like if you mix salt water and you get a spoon and take a spoonful of it, it's going to taste the same as if you took a spoonful from a different section. If you tried to do that with sand water, that wouldn't be the case, right? There would be like lots of sand in one spot and a small amount in another. Okay, so how do we actually tell that on like a big scale? It's how they look, basically. So salt water, it looks like the same thing all throughout, right? Assuming you don't put too much salt in. So I put a small pinch or teaspoon of salt in, it dissolves into the water. It looks uniform throughout, right? You can't tell that there's salt in there. It's been dissolved in. Another example would be like alcohol in water. So rubbing alcohol or drinking alcohol, whatever it is, those are both what we say soluble in water, meaning that they will form a homogeneous mixture, or a solution is another word for that when it's a liquid. So ethanol in water, salt in water. Another good example is alloys, metal alloys. So brass is, I think, zinc and copper. They melt it down, they mix it together, and then when it solidifies again, there's a very ordered structure of zinc and copper atoms, and it is consistent and uniform throughout. Stuff that doesn't mix uniformly, you probably can think of easy examples like oil and water. You can put those together, they can form a mixture. This is basically salad dressing, right? Add a little acetic acid, which is the vinegar. You shake it up and it looks for a second like it's uniform and then it divides, right? These are probably easier to identify. Sometimes people might think like, oh, okay, concrete. Like that seems pretty uniform, doesn't it? But if I take a section of concrete from one part of the sidewalk and another part of the sidewalk, this one might have like a big fragment of rock in it, and maybe that one is pretty consistent and only has small little grains of rock, right? Like over a large portion of it, it's not actually consistent. They just have broken them up into small enough chunks that it looks like they're all the same throughout. We'll try to give you examples that are pretty obvious. So if you shake it up and let it sit for a second and it looks different, it looks like it's two separate things, then it's homogeneous. Okay. That stuff feels kind of boring. I think we have a little bit longer than I had to do the unit stuff. Any questions up to this point? Because we're going to kind of switch gears and go to more mathy stuff. Okay. Obviously, this is a science class, so we're going to use the metric system, or what's more appropriately known as the SI units, standard units. I don't like that this says base units, because when I think of a base unit, I think of a thing that doesn't have a prefix. So when I think of base units, I'm going to be talking about grams, not kilograms. But technically, the normal unit that's used in scientific communities, we think of it as kilograms. That's just because the stupid physicists and stuff are, working on a bigger scale than us a lot of the times. Not always, though. Plenty of physicists work on small scales. I don't know why we use that, because it's what we're familiar with. We don't weigh ourselves in grams. We would weigh ourselves in kilograms. Or pounds, or stones, if you're British, I guess. Okay, so we're going to be working in terms of meters, grams, seconds, obviously. The temperature we're going to be working in is Kelvin. We'll get to conversions for that in a bit. I'm going to skip one slide for now and skip forward to metric stuff. So on the exam equation sheet, you'll notice that I give you plenty of English to English conversions, like feet to meters, or I don't think I give you quarts in a gallon, it's 4, but I would give it to you if you needed it, okay? So I don't even expect you to know English to English conversions. That would be like 3 feet in a yard. I would, though, expect you to know metric to metric conversions. So the ones that are starred, you have to have those memorized. So if I tell you, 10 kilometers, I need you to be able to convert that into meters, or for that matter, into centimeters. I also will never require you to convert between English and metric without giving you the conversion factor. So on the previous slide, we'll get to that in a second, that converts between centimeters and inches. So it's going from an English measurement to a metric measurement. I'm going to give you those conversion factors if you have to do a problem. These are the only ones you need to have memorized. Okay, so I've interpreted these in terms of a conversion factor. So what do I mean by conversion factor? Let me take a break for a second. Since I'm recording this, I'm going to keep writing on this side so that my voice carries to my iPad. Okay. Something we're all familiar with. 12 inches is equivalent to 1 foot, right? Because they are equivalent, we can use that to convert from inches to feet really easily. Obviously, so let me just add a caveat. Everything we do for the rest of today, you could probably do it in your head, okay? Mostly. the point of today is to teach you the process that we're going to use for the rest of the semester for calculations. So focus in on the process we're going through, not be like, well, duh, I know that 2 feet is 24 inches. Okay? Let's show you how we got to that point. Show you what your brain is doing when you do that conversion. So you have 2 feet and you want to know how many inches that is. So the process I'm going to talk you guys through, and that I have like 3 steps written out on a further slide, is write down the number and the unit of the thing you're trying to, or that you're starting with. Write down the unit of the thing you're trying to get to. And then we are going to find a conversion factor, meaning something we can multiply by that will tell us the answer in the correct units. Okay? So in this example, you know that it's 24 inches, right? 24 inches and 2 feet are the same thing. Agreed? They're just in different units, but they are the same thing. They are equivalent to each other. 12 inches and 1 foot are also equivalent to each other. So if we rewrite this as a fraction, whether we have it in this direction or in this direction, and we multiply that by anything, we're just multiplying by 1 because they're equal to each other. So if we put one over the other, it's like we're multiplying by 3 over 3 or 10,000 over 10,000 or 1 over 1, right? We're just multiplying by 1. And that's why we're allowed to do this, why it works mathematically. All it does is changes the units of the thing. It doesn't change the actual meaning of it, okay? So the way we do this, number and the units we're starting with, the units of the thing we're trying to get to, and then everybody pay attention, this is the important part, okay? Ready? This unit goes on the bottom. This unit goes on the top every single time. It's amazing, okay? You just have to move them from here to there and move it from here to there. And now all you have to do is ask yourself, do I know a conversion factor? Do I know an equivalence that gets me from inches to feet? Oh yes, I do. There's 1 foot equals 12 inches. You put the right number with the right unit and you're good to go. It's great. This is pretty much all the equations in chemistry. Not really, but a good amount of them. So instead of an equation every time, we are going to develop a plan based on the units of how to get from one thing to another. Okay? So then when it comes to doing the math, we just do top numbers multiplied divided by the bottom numbers. Nothing over here, so we don't have to worry about that. That's 1, so we don't have to worry about that, right? So 2 times 12, 24 inches. The units end up canceling, just like if you had numbers that canceled out, units can cancel out too. And so this leaves you with the unit you're trying to get to. So 2 times 12 divided by 1 is 24 inches. So that's the process you did in your head to figure this out. Do I have time for a story? When I was in 3rd grade, my dad was driving a car for one of my sisters who was in college. There's a lot of us, so there's a big age gap. And he let me go with him. And he was like, how much longer is it? He's like, well, it said it was, 100 miles. And we're going 55 miles an hour, 60 miles an hour. And I was like, well, do I divide or do I multiply? Now that I think about it, I'm like, geez, that was kind of advanced for being in 3rd grade. But he explained dimensional analysis to me. He's an engineer. He didn't call it that, but he was like, well, if you have miles per hour, so per means divide. So if you're going 55 miles per 1 hour, you can use that as a conversion factor. So if I have 100, what did I say, 100 miles? If I have 100 miles left and I want to know the hours that's going to take, this goes on the bottom, this goes on the top, and then I put the number with the correct unit. So 1 and 55, and I take 100 and divide it by 55, and that's going to tell me the number of hours or the, fraction of hours that it's going to take. okay? A lot of the times I think you guys are familiar enough that you can just say, well, I know it's not gonna be 5,500 hours, so I know I'm not gonna multiply. But when you're doing chemistry, it's not intuitive. You're not gonna know whether your answer makes sense or not because it's something you're unfamiliar with, and that's probably why people struggle so much. Okay, back to metrics. So you're gonna have to know the prefix and its associated multiplier. So if I say that the multiplier for kilo is 10 to the third, what I mean is that 10 to the third of the base unit, meters, is equal to 1 kilometer. The base unit for nanometers, we'll use this one in a second, is 10 to the not the base unit, the multiplier is 10 to the negative ninth. If you are shaky on scientific notation, this is basically scientific notation, we're missing the 1 times 10 to the third. We don't have that 1 in there. If you're shaky on that, on Pearson, it's an optional assignment. It's just called like Math Primer. And there's a bunch of different topics in there. You can go in and review pertinent math topics for Chemistry 1. Okay? Because I'm not going to necessarily explain it all in here. I'll give you little like reminders. Okay, so let's go ahead and do this next problem. The one up here is very similar to what we just did like 2 different times, so I'm not going to use this example again. You can use it as an example if you want another separate example. Okay, determine how many meters are in 294.5 nanometers. So here's where I write down the 3 questions. What is the unit of the thing that I'm starting with? And I would say, what is the unit and number? What is the unit of the thing I'm trying to get to? And what are the conversion factors I need to get from one to the other? So when I look at this question, I'm not even going to read the question. I would say 70% of the problems that are like this, you could get right without even understanding what you're doing. That's not to say that you shouldn't understand what you're doing, because there might be a follow-up question or something. But if you use this approach, you're probably going to be able to get the right answer without even really knowing. So like ignoring all the other words, I'm just going to pick out, here's a unit, here's a unit. This one has a number associated with it, so that must be where I start. So I'm going to start with the number and the unit. I'm going to say equals the unit I'm trying to get to. I'm going to put this unit on the bottom, this unit on the top, and then ask myself, do I know a conversion factor that equates meters and nanometers? You'll be like, yes, it's metric, so I memorized it, right? So let's now interpret what that multiplier means. 10 to the negative ninth meters equals 1 nanometer. That's what that multiplier means. So 10 to the negative ninth is this, 0.80, 1. So a very small fraction of a meter, 10 to the negative ninth meters equals 1 nanometer. A nanometer is really, really small. Another way of saying that, not to confuse you, but another way of saying that, 10 to the ninth is billion. So there is a billion nanometers in every 1 meter. Think of a meter stick, right? It has 100 centimeters in it. It has 1,000 millimeters in it. So if you had a meter stick, there would be a billion nanometers in that meter stick. Okay, so I'm going to take this equivalence and turn it into a conversion factor. 10 to the negative ninth will be tied with the meters, 1 will be tied with the nanometer. So 1 nanometer, 10 to the negative ninth meters. And then I just put it in my calculator. Why don't you guys actually get out your calculators? If you have your phone this time, I'll forgive you, but I think I said this in here. You really want to use the calculator you're going to use on an exam for everyday problems so that you're familiar with the because I'm not gonna let you use your phone on the exam.
Is it reasonable to use Desmos scientific?
No, because you're gonna be putting, I mean, we're gonna have like 10 to the 23rd, so you're not gonna wanna put in, you know, yeah. So definitely you wanna, and maybe I'll just do this on my calculator too to show you guys, you know, how I would input. I will say everyone's is gonna be slightly different. So there's kind of two ways that you can approach this, but let's go ahead and do it. So 294.5. And then I'm going to multiply this by 10 to the negative 9th. So I'm looking at this one here. Yeah. So there's two ways I can do this. I can put in 10 and I can raise it to the power negative 9. Or there's almost certainly a button here that does that for you. So you just do, in my instance, I do shift and hit this one. And then it would put 10 and I'll put negative 9 in there. When you have a number in front of it, like 3 times 10 to the negative 9th, you can do quantity three times 10 to the negative 9th, okay? If you do that, you want to put parentheses around it. You will totally screw yourself up if you try to just do it like this. When you start to get into division, you'll end up dividing by 3 and then multiplying by 10 to the negative 9th. The other option is a lot of calculators have a function that is scientific notation. And if you do it this way, it'll look like that. It's a capital E, not a lowercase. Lowercase e is a number, it's a constant. It's a capital E, and that implies, sorry, negative, that implies 3 times 10 to the negative 9. Okay, so I'm gonna do it this way, times 10 to the negative 9th. So then it tells me it's 2.945 times 10 to the negative 7. It spits it back in true scientific notation, where it's number, decimal, the rest of the numbers. If your calculator is spitting it back to you as 0.0000002945, I would figure out how to tell it to give it to you in scientific notation. Okay, so that is the amount of meters in 294.5 nanometers. So we'll start on this last page on Friday as like a warm-up. Hang out if you have technology questions. I'm happy to help you with it. Today's the last day. I'll probably be patient about it. So I might as well take advantage. Yeah, it took me a second to be like, well, I mean, I guess you could have 8 zeros. And I was like, no, 23 would be a problem.
Mine's going out like that.
Yeah, so that's, well, it should be to the negative 7.
Oh, was it to negative 7?
Let me see why. Because you have 10 times 10 to the negative. So you put in 2 negatives. This is exactly the same calculator that I used all through high school. So you would just want to have that. You actually have like 10 times
Okay,
10.
so I put it in like 294.5 times.
Oh wait,
second
clear
log.
that. Okay, there, go ahead.
294.5 times second log, and it was
Negative 9.
I think it's like
Yep, there you go.
Okay,
Yep.
perfect. Thank you. But
Uh-huh.
most of the like.